Thank you very much for joining us. My name is Seamus Garvey. I'm a professor at the University of Nottingham. I arranged some time ago for Grant Wilson of the University of Birmingham to come and give a talk at the University of Nottingham because we have some common interests, some small disagreements, mostly agreements, and we were very eager to find out about what Grant knows and to share what we know. Grant is a lecturer in chemical engineering at the University of Birmingham and also a board member of the IMechE's Environment and Sustainability Group. He leads the Energy Data Analytics Group at Birmingham, whose activities include analysis on energy system flexibility and using multi-vector, multi-scale data analytics. His previous work has included the UK Energy Research Centre's FlexiNet project that gave new insights into sub-daily demand variability, and per day flexibility of local gas networks. Additional research includes modeling the need for thermal energy stores and the analysis of local data sets for a regional energy systems operator project. Grant believes that there should be a greater focus on the underlying needs for flexibility in future energy systems throughout policy, industry, and academia, and I agree with him 100% on that. I can tell you this isn't written down. Grant is a thrill seeker. We didn't have him logged in until 16 minutes past 5, so a kindred spirit in that respect as well. Grant, over to you. So, Grant, sorry, beg your pardon, just one more moment. We're going to run this slightly differently from a normal seminar, so please can everybody online mute if you're not already muted, and you will be able to pose questions for Grant through the Q&A box. And Grant may stop at one or two points in the middle of this, and if he does that, I'll relay some of the questions that have been asked. Okay, go for it, Grant.
Well, great, thank you. I'm going to now share my screen. Thank you for the warm welcome. So while I try and do this, what I'd like to double check, if I can double check with you, Seamus, initially, you can see PowerPoint first page, and you can see a laser pointer there.
Yes, to both of those questions.
That's brilliant. Okay, well, just to your point about thrill seeking, I think probably less to do with the thrill seeking, more to try and find emails at the very last minute in terms of the link into this particular thing. But there we are. Technology is a wonderful thing, and it is a wonderful thing, allowing us to carry on even in the conditions that we find ourselves in. So without further ado, we'll carry on. So firstly, I hope everybody's fit and well. Massive thank you to Professor Garvey for the invitation to give an Energy Technologies Research Institute lecture. I've had a look at the very prestigious panelists and people I've had on before, so I'm absolutely delighted to be able to give this talk. I'm passionate about the need for empirical, measured multi-vector energy data, basically not just electrical data, to help us understand the challenges that we have ahead. I believe this set of slides is going to be made available to everybody. The graphics are all badged with Creative Commons licenses. You don't need to get in touch with me, just use them. Please feel free to use them if they're helpful to other things. And finally, I've got a bit of a tickly cough I've had for a couple of days now, so I may put the microphone on mute from time to time. It's not a problem with your speakers or line, it's just I've put it on mute to have a right good cough, okay? And just to see, yes, I can do this on the, so there we are, start off with a cough that I can mute. So I lead the Energy Data Analytics Group at the University of Birmingham in chemical engineering, and under the Birmingham Centre for Energy Storage, also the Birmingham Energy Institute as part of. This is looking at multi-vector, multi-scale data analytics. Current projects I'm involved in at the Active Building Centre and looking at the case for thermal energy storage to help decarbonise GB energy systems, and also recently sort of started a West Midlands Regional Energy Systems Operator project. That's an Innovate UK project, with Coventry City Council and a bunch of other partners in that. It's quite interesting to look at local area data sets as opposed to what typically we're going to look at in this presentation, which is national level data sets. So the presentation structure, we'll have a look at the changes in Great Britain electrical generation since 2009 to help set the scene for some of these things. Sorry, I'm just trying to get some screen space. The impacts of COVID-19 measures on the electrical system using 30-minute data. We can also already see changes to that. Have a look at some supplies and demands of GB energy vectors, electricity, liquid fuels, natural gas, using daily data, and that provides us with a sense of scale around some of the challenges that we currently have, how we manage that, and that might help us to think about challenges in the future. We're going to have a look at comparison of peak demands between the natural gas and electrical networks using hourly data as well, and then focus in particularly on a challenge, a significant flexibility challenge, which is a 3-hour 5 a.m. to 8 a.m. difference in local gas demand, and we can have a think about that as a challenge going forward. So as an introduction, past decade has seen significant efforts to decarbonise the electrical sector in Britain. We know shifting away from coal, reducing energy consumption, and increases in weather-dependent renewable generation have provided real benefits in terms of the reduction of the electrical sector emissions. Excuse me. So we also know through the 2020s, this, let's say, like thorny energy challenges are located in decarbonising heat and transport, with heat providing the greatest needs for overnight and seasonal forms of flexibility. And that is what we'll have a look at through this presentation. We're going to have a look at existing levels of these energy supplies and demands, and what this might mean for different forms of energy system flexibility, including overnight and seasonal storage. Won't go into too much seasonal storage because we don't have time, but there's a tiny bit at the end. So all data underpinning this presentation is based on measured data from electrical and gas system operators. That is important from the perspective of, if you don't believe them, then who do you believe, frankly? If we look at model data moving forward, clearly that is based on quite a bunch of underpinning assumptions. And therefore, when we are modeling, we have discussions as modelers to understand what are your assumptions, what are the underpinning efforts that you've put into the modeling, how does it work? And therefore, you have to understand the model and the assumptions prior to even understanding what the model is saying. That is less to do with an issue with historical data. It is what it is. You either believe it or you don't. I do, because it's the energy system operators that have provide this. They're a presentation of the flows of energy and looking to provide greater clarity in where we're starting from. This is not to say where we're going to. It's not a prediction of how things are going to be. It is merely a point of this is where we are starting from. We have 30 years to transition to a net zero society. And in 2020, this is where we're starting from. So it also throws up some of the challenges will need to be overcome as well. So very quickly running through, this is in a nutshell how the Great Britain electrical system has decarbonised over the last 10, 11 years. Excuse me. What we can see there, broadly speaking, is we've had a significant reduction in the top line. We've had a significant reduction in the overall electrical demand. If we had not done that, it would have been even harder to bear down on things such as coal and to effectively take market share away from things such as coal. We would have still had to find enough electricity to deal with this particular demand up here, but we haven't. We have reduced our electrical demand over that 10, 11, 12-year period. We can also see imports. This one is biomass, solar and wind, in effect have squeezed coal off the system. Now, there's a whole bunch of other things that have happened, but if we look at it in the round, in essence, that's broadly what has happened. There are different ways of portraying this. This is a very quick way of looking at wind in particular, and to see the size and scale of the wind increase over the last 10 years. So in 2009, down here, this is looking at, these are the number of days of the year, and this is a cumulative sum throughout the year, and ending up with however many it was, just under 10 terawatt hours in 2009 that wind provided. So we can go through that. To have a look at 2010, we can see the steady increases all the way up 2012, 13, 14 and 15. And then interestingly enough, and this is one of the things that we should not forget, it's pretty obvious when we think about it, there's an annual variability to wind as well. So 2016 actually ended up providing less wind overall in the entire year than 2015, even though clearly wind would not have come off in terms of capacity. In essence, or it's very likely that even additional capacity was in place in 2016. So this helps us to think perhaps a little bit more about the seasonality when we think about multi-year seasonality as well with wind. So then we go back to, 2016, big jump up to 2017, 18, 19 was last year, and 2020, we are on for, I would say, pretty clear. It would be highly unlikely that it would finish less than 2019. It's going to be another record year. We can see down here, this was February. If we remember back to a point before COVID, the storms through February, 3, I think, came through back to back, and this caused a record month in February at over 8.5 terawatt hours, supplied 33% of the electrical demand. So a whole bunch of records got broken in February, and even in this quarter, actually, there's a couple of things as well. So that is just another way of displaying the electrical system has been subject to considerable change already. This is another way of looking at it. Goodness me, that is a bit bright on my screen. I'm not sure if it is on yours. Or maybe tone down the nuclear color next time, the red at the top. But really what this is looking at, this line here is a 50% line of all of these adding up to effectively over than 50%. All of these are low carbon. We have solar at the bottom, hydro, wind, biomass, and nuclear. Excuse me. And we can see actually 7 out of the last 8 previous months were greater than 50%, knocking on for, and even February, it was over 60% of the electrical generation in GB was low carbon. November was a low month wind, sorry. Yeah, a low wind month, sorry. I just wanted to put this in really quickly. Myself and a couple of colleagues had a look at this just very recently. This is the last, in essence, 4 weeks prior to this week of electrical demand in Great Britain. Starting off with the first week in March is the green line, then the purple line, then the red line, and then the blue line. And this was just our curiosity to understand what was already happening in terms of COVID and the measures, the social distancing measures. So if we remember back even past a week ago, and Boris Johnson announced on the Monday evening about social distancing, pretty much immediately the next day, the blue line started to track down and started to look in shape and level pretty much like a weekend day already. So this is already having a significant effect on the electrical system. I believe there will be even a greater effect on the liquid fuel system, but we'll come to that a bit later. So just to finish off with this, setting the scene about the electrical system already being under considerable change. In 2020, Q1, sorry, just finished a couple of days ago, solar and wind combined generated 33%, so a third of the electrical generation over the quarter. And this, for the first time, just beat coal and gas. So just solar and wind, not biomass and not hydro, just solar and wind managed to provide greater amount of electrical generation than fossil fuels combined for the first ever time. Also, 2020, the March, it's the lowest March electrical demand since 1975, we believe. And if this continues through April, which it looks as if it will be even lower than normal as well. It'll probably take us back to a time for a month of April back into the 1960s. And that is truly remarkable. Notwithstanding COVID, that level of increase in the amount of population since the 1960s and 70s, the amount of buildings that have gone up, also the amount of information and communication technologies that as a nation, we are not using as much electricity, and it takes us all the way back to that. So the question then is, should we congratulate ourselves on that and the reduction in electrical demand and the progress of decarbonising the electrical grid? Well, perhaps yes and perhaps no. So we could have done more, particularly around building regulations. We've offshored the manufacture of some goods and services. We are importing emissions, we're importing electricity contained within them, as it were. And thus, if we look at a consumption-based emissions approach that John Barrett and his teams continue to do up at Leeds, then we're not doing anywhere near as well as decarbonising in terms of electricity. And as we're about to see, when we start looking out with the electrical system, we still have an awfully long way to go. So low carbon flexibility, is just to raise this sort of slightly earlier on in this presentation. We're doing well on low carbon generation. I think there is an argument for that. But what about low carbon flexibility? If we think forward in terms of a fully decarbonised net zero energy system, then we not only need low carbon primary energy generation or harvesting or supply, whatever you want to call it, we also need a source of low carbon flexibility. We need those two things to have a fully decarbonised electrical system. So research and development is rightly shifting to a focus to low carbon flexibility over different timeframes. And then we're going to have a look at heat and transport, because these are the ones that actually at the moment, they are less dependent on the electrical system. They are far more dependent on the natural gas system and the liquid fuel system. So we're going to have a look at daily demands and supplies to get a sense of the scale and seasonality. So this chart is just 4 years worth of daily data. So it goes from 2016 to pretty much yesterday. I'm going to try and move this off again. Don't think I can, so I can't actually see over to the right-hand side of this myself because it's covered. Oh no, there we are. The red line at the top, just so people, and to explain what we're looking at here, this is an entire year. There's 4 and a bit years worth of data. In the summer, we have a lower overall electrical demand on a daily basis than we do in the winter. The winter, however, we can see there's significant drops down over the Christmas and New Year holiday period. There are a dip. If we stretch this a little bit, you would see a dip, 52 of them pretty much in a year. So the dip is every weekend because the Saturday and Sunday is lower as an electrical demand than the normal working week, the Monday to Friday. So what we're looking at there is winter, summer, with every weekend, excuse me, showing, and the holiday periods. We can also see actually over here, this is bang up to date, that the significant drop off since the COVID-19 measures started. The green line is the equivalent, this is electricity from low carbon. So this is wind plus solar plus biomass plus hydro plus nuclear. And this is all of that. So in essence, the percentage that we talked about earlier would be contained within this. Moving on from that, normally when I'm presenting this, I get nods from people in the audience, but clearly that's not possible now. So I'll just shift on anyway. What we have here is in the same scale of, I'm sorry, I should have pointed out, this dotted red line here is 1,000 gigawatt hours a day, a terawatt hour a day. That's pretty much at peak times during winter, thereabouts. The electrical demand of Britain is about a terawatt hour a day, above or below. Interestingly, actually, if we go back one slide, because it's been a mild winter, because perhaps of a few other things as well, the electrical demand on a daily basis, this entire heating season that we've just been through, I think it never got above 950 gigawatt hours per day. So that's really quite a drop from previous years. Moving on to looking at liquid fuels from the perspective of a daily basis. The reason that these are blocky is because the original data comes from BEIS, the Department of Business, Energy, Industrial Strategy, and it's available on a monthly basis. So therefore, to make it into a daily basis, I just divide it by the amount of days in that particular month, and that's why it looks rather blocky. So transport motor spirit, that's petrol. What I've done over here, this is estimated data, I might say. This is not actual data because it's always 3 months pretty much in arrears. So the last time the data is actually okay is December. We will need to update these as the other ones come in. The drop there is my estimation of it being 55% of the previous month. So all that is just a straight drop of 55%. Sorry, the drop is 45%. The total amount is 55%, just to see what it would look like. But that is petrol. We pretty much use, if you compare it to the amount of energy that goes through the electrical system on a daily basis, about half we use in petrol. Clearly, they're not the same thing. One is chemical energy, the other is electrical energy, and the exergy between them is very different. Looking at aviation fuel, we can start to see it's about the same as petrol, but actually there's a bit more seasonality underpinning this. We can see that there is more demand for aviation fuel in the summer than there is in the winter, and we would naturally think that seems fine. Equally, going back a stage, sorry, I should have pointed out, on a monthly basis, and that does hide a multitude of flexibility issues, it does seem that transport fuels are fairly flat. They're not significantly seasonal. When we certainly come to have a look at the gas demand in the future slides, that becomes pretty obvious. So aviation fuel does have a little bit of seasonality. And then we're looking at DERV, which is diesel. So this is diesel cars, agriculture, heavy goods vehicles, everything as well. So it's about double petrol and double aviation fuel. Broadly speaking, it's about the same level as the electrical demand. If we add all of them together, we have to shift the scale, the axis, the y-axis, just to get it all to fit in. But the red line and the green line are all the same. It's just on the left-hand side, the axis has been increased just to get that in. But that's now when we're looking at all liquid fuels together, that is petrol plus diesel plus aviation fuel. That is the sort of scale and level in relation to the electrical system as we currently have on a daily basis. When we start to look at gas now on the same scale, then we have the transmission level for gas and also local gas. So at the transmission level, we have bigger industry connected directly to the transmission system. And that is the series that you're looking at the bottom there, this gas to industry. So a couple of things that would perhaps suggest is equally, again, it's reasonably flat throughout the year. And secondly, it's perhaps less large than we might have expected it to be. you know, these are, we naturally think that big gas users use a lot of gas, but when we actually compare it to other things, perhaps it's a little less than we thought it was. So that is gas to industry connected at the transmission level. This is not gas which is connected at a distribution level, industry that is. This is gas to storage injection. Partly it's, you know, a bit of a mess. I'm not going to go into any detail on this other than it's there, it's reported, people can have a look at it effectively for the sake of completion for the slides. This is also gas to power stations, which is taken directly from the transmission system as well. Equally, just to give a sense of scale of that. Clearly that goes in to power stations. Broadly speaking, 50% of it comes out the other end as electricity, give or take. So moving on and shifting down the axis again, just to be able to fit everything on. We are now, instead of looking at a terawatt hour here, we've shifted this up so we can look at things going up to 4 terawatt hours and 5 terawatt hours of energy a day. And the things that we are now looking at are the two fractions of the local gas demand. So we have the transmission system for natural gas. At certain points, local gas or gas distribution networks connect to that and take gas off the transmission system. And then they deliver that through to end users. The reporting of that is broken down into two fractions. One is called daily metered and the other is called non-daily metered. And pretty much it's, you know, the name is very descriptive on that. If you have an a gas meter that provides a meter reading on a daily basis to the gas distribution network company, then you will be under the gas daily metered. And if you don't, if your gas meter has historically, before smart meters, was measured once a quarter or once a month, so domestic properties would all be contained within and under this series called gas non-daily metered. So when we look at and think about, and back to the title of the lecture or talk, the presentation is the decarbonisation of space heating and hot water, then this is the fraction of energy, primary energy, going into the UK system at this point in time. That is certainly providing a significant amount of space heating and hot water. And also the flip side is true, space heating and hot water demand is providing a significant fraction of this series that we're looking at. So a couple of things to point out with this is that in comparison to other primary energy demands on a daily basis, that is, that the gas non-daily metered series is the one that creates the most amount of seasonality in terms of the overall demand or supply, however you want to look at it, for Great Britain. And if we step back a moment and we think about why that is, it becomes obvious to us that because space heating is a major fraction of that, it's much colder in the winter than it is in the summer. The demand for space heating, therefore, is much greater in the winter than it is in the summer. Therefore, the energy that goes to provide comfort levels for us all is much greater in the winter than it is in the summer. So it all tracks through. Just to point out, that was the beast from the east on the 1st of March 2018. And we can see, looking at this is daily data, that there's really quite a significant peak there in comparison to other things. And we'll come back to that in a bit. Total gas demand, excuse me, is this blue line now. So this is basically Great Britain. If we add up all the transmission plus the local gas demand, so this is in effect everything other than exports of gas. This is the blue line, and that is what GB has used over the last few years, in essence, to provide it to keep in business. So this chart, actually, I do tend to like to put all of these onto one chart. You have a blue line, sorry, a green line at the bottom, just to provide a sense of scale on how we're doing, and that is low carbon electrical generation. You then have the red line, which is the electrical system, the amount of demand on a daily basis going through the electrical system. But let us not forget that actually, to keep things going, to keep us in business, to keep us warm, to keep things transporting around, we also have the grey line, which is liquid fuels, and we also have the blue line, which is gas at the moment. So this is our starting point. This is where we're, starting this 30-year journey. Can I just ask on time, how are we doing actually?
Grant, you're 35 minutes in, and keep going. You take another 15 minutes?
Yeah, okay. Yeah, no, that's fine. I might need to speed up a bit. So the previous slides show major swings in non-daily metered gas demand over the season during a week, the greatest source of seasonal variability. We're going to have a look at hourly gas data to see with the within day swings in terms of energy supply or demand. Excuse me. But before we do, it is worth sort of stepping back a moment and thinking, depending on the quarter, domestic gas use as a fraction of local gas demand, because on the next few slides, we're going to be looking at local gas demand, which is the daily metered plus the non-daily metered. Domestic gas use, which will contain space heating and hot water, clearly just for domestic, is circa about 40% over Q3, the sort of warmest time of year, and is about 60% in Q1 and Q4. So when we're looking at the blue line on the next few slides, it is not all heat. It is not all space heating. It is not all, or certainly rather, it is not all domestic space heating and hot water. It's just everything that's contained within the local gas system. So we're going to look at local gas demand, just to run through quickly. It's not, it does not include, the data set doesn't include high pressure gas transmission grid, interconnectors, power stations, storage and industry. The gas demand was originally in units of 1,000 standard cubic meters. Excuse me. We know that calorific values do change, but for the purposes of this analysis, we just kept everything at 11 kilowatt hours. Per standard cubic meter of natural gas. It's the hourly gas demand from final users connected at the distribution level. So all domestic heating, cooking, hot water, as well as smaller industry, commercial, service sector too. And equally embedded combined heat and power plants will also be contained within this value. So indebted to UKARC for the funding for the FlexiNet project that I led a work package that helped to develop this. And the gas distribution network companies that provided the data, their operational data under a bunch of non-disclosure agreements as well. So cutting to it, what we're looking at here now is stretched out to a week. This is the red electrical demand that we saw previously, but not in energy terms. This is now looking at it in power terms. However, this is not in half hourly, it is actually in hourly. So it's the same values in energy terms as well, but we chose to actually display it in power. So you can see Monday, Tuesday, Wednesday, Thursday, Friday, fairly typical, lower Saturday and Sunday, and a fairly typical electrical demand profile with a peak during the day and an overnight low. This is the gas distribution network. So for all of the Great Britain, 4 gas distribution network companies, all of the data added together, aggregated, this is what it looks like in terms of local gas demand. Now, there's a couple of surprising things to me personally when this sort of jumped out of the box when I first started looking at it. One was I just naturally expected things not to be quite as spiky in the summer because of space heating. So I was a little bit surprised at actually how spiky it continues to be even in the summer. And perhaps, you know, that's a question, an ongoing question I have as well. But broadly speaking, it's of a similar sort of level to the electrical system. In the summer, the gas system is delivering, by and large, broadly speaking, similar sort of levels in terms of sort of peak power, give or take. So I'm going to try and see if this will work. Seamus, can you see that? Thumbs up if you can. Okay, thank you. So this is using the same data, and it's actually layered on here as well as the temperature at the top. So this is actual data, this is national level electrical data, this is the local gas demand data at the bottom as well. So if it was just the summertime that we had to deal with, then perhaps we could think about that in a different way. However, this is now into, you know, well into the heating season. The local gas demand has significantly increased. The flexibility that we need to underpin that has significantly increased. This was actually the beast from the east day here. And when we look at just the raw data for the amount of energy transferred through, and we'll come back to that in a minute, through the electrical network versus the gas network as well, or rather just the local gas network. The transmission network is delivering more gas to industry and power stations at the same time. But we can see the peak here is 214 gigawatts. So that is, broadly speaking, about 4 times the amount is going through the electrical system at peak as well. So that is, it's an interesting sort of figure in its own right. But the ratio, I'm going to say now, because I know what's coming up, is only 4 times. So if we had to think about shifting, in essence, the blue line over to the red line, and what we would be doing by doing that, we would be using heat pumps, resistive heaters, we would be electrifying heat. We could take a bunch of the blue line and we could put it onto the red line. Now we know with coefficients of performance, with heat pumps in particular, that we're not taking, it's not a 1-for-1. We're not taking 1 unit off the blue line and putting 1 unit onto the red line. So we've got an advantage there. But this is just looking at the week, the peak week of the beast from the east, with local gas data and electrical data. So we can see, excuse me, there really is quite a regular, Monday, Tuesday seems to be a fairly regular pattern of local gas demand. You've got a double peak, you have a big drop in the middle, you have a very significant drop overnight, and you have a wider delivery of energy effectively in the evening than you do in the morning. This was an unusual day, the Thursday of the beast from the east, and the Friday as well. What we thought was actually going on here, because snow shut quite a number of the schools, we believe that because people were at home, it was very, very cold. At least if one family member was at home because of children were at home, then the heating would have been on. So the drop off in heating, gas-driven heating, did not happen to the same degree on that Thursday. Interestingly enough, if we remember back to the daily demand chart, then there was really quite a significant increase when we looked at it through the lens of a day at a time. But when we look at it through the lens of an hour at a time, there isn't a very, very significant increase. There is an increase, but not as significant as the daily amount. There is an increase in the power over an hourly basis, but the things that made the day have a much greater level of demand was, we can see that the overnight didn't drop off to the same degree, and certainly the middle of the day didn't drop off to the same degree as well. So these are some of the things that we might consider to think about in future when we're setting up networks and energy systems to deliver heating and hot water. But just quickly to draw attention to this 5 o'clock to 8 o'clock increase in demand. So this is, in essence, this is the delta of the energy. This is the rate of the difference in demand over that period of time. When we compare that between the electrical system and the gas system, and albeit this is the day before the beast from the east. So this was the 28th of February. On a 3-hour period, just the increase, not the total amount, just the increase happened to be 116 gigawatts, or rather plus 116 gigawatts on the gas system. And at the same time, the electrical system was delivering an additional 11 gigawatts. So this is the point I was making just a moment ago about when we look at just peak. So the peak here to peak here might be about 4 times. But when we look at the systems that are set up to deliver energy and the rate at which they can deliver energy and the shared, the amount that they can share that, deliver that, we're now into the realms of 10 times. So that is equally something that we might wish to consider. Yes. Seamus, yes, I think so. Another 10 minutes if people can bear with. I will maybe eat in a little bit to the question time, but we'll try and get this through. So, oops. So one of the questions was, and indebted to Jim Watson of IMechE of asking this question actually straight away, when we initially were sort of presenting this, was, okay, well that is really quite a large amount, but how representative of it? Is it just because it was the day before the beast from the east? Is it an outlier? So what we're looking at here is for every day over that 11, originally we had 11 months worth of data for this to compare between the electrical system and the local gas system. And what we're looking at on this chart is basically the 3-hour, only the 3-hour difference in energy. So this bit here was the peak that we've just talked about, is the 116. And at the same time, the electrical system over the 5 o'clock to 8 o'clock period was delivering an increase of 11 gigawatts. So interestingly with this, it does seem that if we take a value of 80 gigawatts or plus 80 gigawatts, it's really not uncommon for the local gas system to be delivering an increase of energy over that 3-hour period between 5 o'clock in the morning and 8 o'clock in the morning of above 80 gigawatts. So pretty much, one can maybe suggest that's pretty much business as usual. I'm sure if we dug into this, we'd find that many of these with lower elements are probably a Saturday and a Sunday. So if we said just a business working day, what we would find is the delivery of energy, the increase, the rate of increase, or rather, is over 80 gigawatts in our current setup, in our current framework. And that might give us some indication of the levels of flexibility within our systems at this point in time. So that leads us to think, okay, well, how is this happening? Why is this happening? So we dig into it, we know, and we understand that the gas pipeline infrastructure is just very different from the electrical system. It's inherently very different. It has a capacity to store energy actually within it, because it is a pipeline and because the vector, because the material traveling through it is a gaseous vector that we can increase the pressure of overnight, and this is exactly what happens. It's called line pack. So additional gas can be stored closer to final end users overnight, ready for this sharp increase in their demand at 5 o'clock each morning. And that gas system just deals with that at this point in time, because it has that level of sort of inbuilt flexibility to it. It has the capacity for significant levels of inherent storage by changing the pressure of the gas. We also did a follow-up briefing note within IMechE, and it's based down here for people to perhaps go to have a look at. But just to point out, on the table within that, it explains what line pack is, the levels, etc., etc. But two sort of standout elements for me in particular in this were just looking at the local gas networks alone, and this was equally focusing on this level of overnight flexibility. So in essence, the line pack, I'll try not to spend too much time on this, but what we did was take how much energy is stored in the pipeline at the sort of peak time overnight, and what's the lowest amount of energy it goes to during the day. And the difference, the sort of delta between the peak and off peak as a state of charge, that provided this within day line pack flexibility, we're calling it. So then what we did is look at every day and then see, okay, well, every day just over the heating season and every day over the year. So every day over the year is lower on average, because the summer, the system operators don't need as much overnight storage, so they don't use it. But looking at the local gas systems between October and March, the heating seasons, for over 50% of the days, the overnight flexibility, the local gas pipelines are providing 220 gigawatt hours of storage. And yes, that's not electrical storage, that is gas storage, it's chemical energy storage. But nonetheless, that is quite a significant amount, particularly if we track across and look at the other red circle. If we look at exactly the same October to March and analyze what was happening on pumped storage systems, then it's never greater than 11, or sorry, it's greater than 11 for 50% of the days. And therefore, you know, we get to understand, okay, we've got pumped storage on our system on the electrical side, but we've got storage inbuilt onto the gas side at that point in time. I should point out, they're not direct comparisons. This is just a sense of scale issue, because actually the flexibility that underpins the electrical side is not to do with pumped storage. It runs out of energy reasonably soon in comparison to, you know, the 900 gigawatt hours that we need to keep going in over a daily basis. What does underpin it is the ability of dispatchable generation. Used to be coal, going back to the initial part of the presentation. It's certainly less to do with coal now, it's more to do with combined cycle gas turbines and biomass to a degree, perhaps hydro as well, but much smaller degree. But these are the dispatchable elements to ramp up and ramp down the output, or rather to match the demand, which is ramping up and down. So in essence, just to make the point that it is still fuels that are underpinning the flexibility on the electrical system at this point in time. But that's a wider question. That's another discussion as to fuels. But really what we're looking at here is equally just a sense of scale, in terms of this is something that perhaps we don't have as much visibility of in the gas system, but nonetheless it provides a great deal of within day or overnight flexibility of the energy systems that we currently have. So why is it important? Back to that point again, with no inherent means of storing electricity within the delivery infrastructure itself, the electricity cables, we have to provide the flexibility on things that are connected to the electrical system. It begs the question, how are we going to manage the 5 AM to 8 AM difference in demand in future networks without a use of gas that is compressible? That's just an open question. It's an open research question, apart from anything else. Energy networks are designed, built, and operated and paid for to cope with peak demands as well as average demand. And that itself, I think we shouldn't forget that. So when we look at the values, we can see gas and electrical demand, average demand, have been dropping over the last decade. That's to be applauded. That's a good thing. But we don't know necessarily if the peak demand has dropped as well. Because actually we want peak demand to be there. We want the facilities to be there when we need it. So the gas system, for example, has to cope with 6 minutes in a 1 in 20 cold snap. That's what we pay for. So the gas system is set up to do so. And I think, look, it is this issue in terms of a net zero future. Equally, this is an open question. How much should our networks be able to cope with freak weather events, such as a loop of the jet stream driving significantly colder weather over the UK for 10 or more days? How are we thinking about that? So current thinking on decarbonisation of heat and hot water, I think excellently captured came out last week, National Grid Bridging the Gap. There's a huge variety of housing stock, and this is me quoting the italics, across the UK, and no one technology solution is best suited to decarbonise the heating of every household. Existing natural gas boilers, however, must be replaced, and a range of technologies will be available, including heat pump, biogases, hydrogen, district heating, and combinations of these, such as hybrid heat pumps. And I think that does summarise pretty much where thinking is at this point in time. There's a whole bunch of different things that might be helpful to help decarbonise heating and hot water. But just to round off, actually, before we get to the questions, a couple of personal thoughts. One is we need to flatten the curve. Now, clearly that has taken on a massively different meaning over the last few weeks, but from an electrical demand and an energy demand perspective, the same thing is true. We need to think about this. An ask of funders, research communities, policymakers, and industry to need to give this challenge area more resources. This is an interesting challenge on this overnight flexibility, this amount of increase in energy we seem to require every day, day in, day out through the heating season, and this very large uptick in demand. But why do we need so much of that overnight and within day flexibility? Do we actually need it in the system in the first place? What's driving it? What can we do about it? How can technologies such as thermal energy storage help? How can we retrofit? How can the retrofit of existing buildings? How can that help? How can we help to manage? It's not, just perhaps one, the whole bunch of different things that we're going to look at to bring to bear in flattening this out. And I think, look, on a personal view, I think it seems logical that if we flatten a daily demand curve for energy systems in Britain, regardless of whatever energy vectors and energy systems we're going to end up with in the future, be that, district heating, electricity, hydrogen, or bio-SNG, it doesn't matter. Flattening the curve would seem to help with all of those. So it's almost one of these sort of low-hanging fruits. I'm not saying it's easy, but it helps with all of them. It's an underpinning thing. I think the data also shows there's an enormous challenge with seasonal energy storage, but we're not going into detail on that. It would take another lecture or a talk. However, just to point out, some recent work that we've just done in the Birmingham Centre for Energy Storage suggests Britain's lost 200 terawatt hours of long-term energy storage since 2005. And that has been through closure of Rough, the natural gas seasonal facility, the drop in coal stocks, liquid fuels, and nuclear fuels as well. But we're estimating the latter one. But that is a non-insignificant amount of energy that we used to have seasonally at our disposal in Great Britain in 2005. We no longer do, but yet, to coin a phrase, the lights are still staying on. Okay, so thank you all for listening. I hope I've not gone over there too much.
Thank you very much indeed, Grant. I'm just realizing at this moment that I don't know what the online equivalent is of a round of applause. But if I did know, I would invite everybody to join with me in one of those now. You've given us a really inspirational and thought-provoking lecture.
Well, look, it's been my pleasure. So thank you very much for having me, and to everybody who's taking the time out of their evening to listen.